connection. Okay, so if we look back, we have been trying to understand granular flows, and we've really looked in detail at slow flows, and then we looked at rapid flows, dense flows, and in that, we were able to calculate the velocity at every point in the system. Then we have been looking recently at what we call surface flows, and here the idea is that we do a macroscopic balance because we're not really interested in the velocity at every point, but this allows us to study the system as a whole. So last time we were looking at one example in which we said that, okay, supposing we are constantly pouring material and then it forms a heap, then what will happen is that this heap will rise with time, and you will get a sort of profile for the layer thickness. The thickness will be highest here, and then it will decrease to 0 at the end. In this case, of course, this deposition rate is constant, so that's why the angle, this profile remains constant, and this thing heap rises. And we could get how this layer thickness varies and how the angle also varies. And then we started talking about another system that's quite important. And in that, we saw that depending on the rotational speed and various things, you can have different regimes of flow. At the slowest, you have avalanching flow where the whole material moves like a fixed bed up to an angle, let's say this larger angle, and then suddenly the bed collapses and it goes to a lower angle. So then it just cycles between these two, and the flow is a series of avalanches. It's an intermittent flow. And then if you go to higher speeds, then you get a nice continuous flow where there's a flowing layer on the surface, and then over here you have a rotating fixed bed. And then you go to even higher speeds, then there's cataracting. So because of the inertia, the particles get thrown out and they fall like this. And at the highest speed, there's centrifuging where all the particles are just stuck to the walls. And we saw that in this case, you must have the Froude number, which is omega squared r by g equal to 1. That is the centrifugal force is greater than or equal to 1. So in that case, all the particles will just overcome the force of gravity and just remain stuck to the cylinder surface. So Fr is what is called the Froude number. What we want to do today is look at the flow in this regime, where you have this flowing layer like this, and then these lines, they're just like perfect arcs of circles because this is rotating as a packed bed. And so particles go like this, and then as soon as they hit this interface, they enter the fixed bed. There's no relative motion between the particles. They just go around like a solid body until they come to this point, and then because of the other flowing particles, they join the flowing layer. So this is the sort of flow pattern you have. And what you can think of is that here you imagine that this is a liquid and this part of it is just a solid. So below this line, the particles form a solid, and above this line, they are a liquid. So what you can imagine is that there's instantaneous melting as soon as you reach this surface. It flows down here, and then as it comes here, there's instantaneous freezing and it becomes a solid. So this is like, you can imagine water and ice in contact with each other, but magically the ice turns to water over here, and here the water turns to ice. So we want to try and write down what are the equations for the flow in this layer because this is very much what we have been studying, and that is the surface flow. And you can see that here there is erosion because the bed is constantly getting eroded, and over here there is deposition, and because this is, but the interface is steady, it's not changing with time, but still there is erosion and deposition because the bed itself is rotating. Okay, so the rate of deposition here exactly matches the rotational rate, and the rate of erosion here exactly matches the erosion rate, and this angle is set in such a way so that that condition is satisfied. So it's a very nice example of both erosion as well as deposition. Okay, so now what we'll do today is essentially look at how we can analyze the rotating cylinder flow. So this is all what we were looking at last time. If you remember, we looked at this flow on a heap. We were able to find how the layer thickness changes, and then we were also able to find out how the angle varies. Then today we want to talk about this rotating cylinder flow. We spoke about what are the different regimes, and now what we'll do is we'll essentially do an analysis of this surface flow in a rotating cylinder. So that's really what I'd like to do today. So we're going to start with, of course, we just note down what is the date today, which is 18th of October, and this is lecture number 32. We'd like to do one example. Surface flow in a rotating cylinder under operating in the rolling regime. Okay, so that is basically we are going to be looking at this particular case, the rolling regime, where you have a continuous steady flow. And so what we would like to do is, first thing is, we just look at the geometry a little bit. How will we put our coordinate system and all? So let's look at the first many assumptions, but let's assume that the cylinder is half full. So that means this distance is basically the radius. And let's say this is the flowing layer. And let's call this distance as y and this as x. Now we know that cylinder is 50% full. And of course, as before, we have a shallow or a thin flowing layer. That is delta by R is much less than 1. So those are the two major assumptions. And of course, here we have a flowing layer in this. It's very tiny, but let's say this distance is delta. And here you have a flowing layer. So there's a shear flow in that layer. Now the first thing that we'd like to do is to find out what is the deposition rate. And from what I discussed a little earlier, we know what is the deposition rate because it exactly must match what is the rotation rate. So we know the deposition rate is just defined as equal to minus Vy at 0, which is the interface. So we have to know what is Vy, and if we say delta is very thin, so we can just say that at y equal to 0, we want to find out what is the velocity. And so this Vy at x equal to 0, at y equal to 0, that means just at that, this is just equal to omega into x. Correct? So this is how the thing is rotating. And so if we look at the velocity in the y direction at y equal to 0 is just minus of omega x. Correct. So this implies that if we substitute, and why is it omega times x? We know that the velocity, let's say for example, if I just draw this a little bigger, so let's just look at only the flowing layer. So here you have the flowing layer. This is y, this is x. So we actually want to find out what is the velocity here. So if this distance is r, then the velocity here is just omega times r. But what we are saying is that this thickness is very small. So we can approximate r is approximately equal to x. I'm sorry, this is minus. This is omega times r. Omega is going this way. This is omega. So this is omega times r is the velocity going inside. And so we have v theta is equal to omega r. And so that gives us that Vy at y equal to 0 is approximately equal to minus omega times x. So this is how I got this. So once we know this, that we have the deposition rate is equal to omega x. That means where x is positive, there is deposition, and where x is negative, there is erosion. So this essentially gives us a very important result which we can use in our continuity equation. So our continuity equation, if we look back in our notes, at steady state, so this is another assumption that we have made, that we are at steady state. So there is no dependence on time. So our continuity equation simply becomes del d by dx of u times delta, where now you remember u is the mean velocity, delta is the layer thickness. This is just equal to minus of omega, and then if we substitute for omega, that is just equal to minus omega x. Now since omega is a constant, we can easily integrate this, and we'll get u of delta is just equal to minus omega x squared by 2. And what we know is that the flux at the end of the layer, that is when x is equal to r, flux is equal to 0. So this is plus some constant c1 when we integrate it. Now u of delta must be equal to 0 at x equal to r. And so that gives us c1 is equal to omega r squared by 2. And so this gives us a very nice result, that the flux in the flowing layer is actually parabolic, and it's just given by omega by 2 into r squared minus x squared. So if we look at the flowing layer, either this or this, what happens is that if you look at the volumetric flux, which is the mean velocity into the layer thickness, it is 0 at the ends. But as you go on increasing, the flux goes on increasing, the flux becomes maximum over here, and then it starts reducing. And that makes sense because you have a continuous input of particles from here, so obviously the flux will go on increasing, and over here you have a constant removal of particles, so the flux goes on decreasing. So here is a one important result. Now the next thing is to write down the momentum balance, because we want to find out both u and delta separately. Remember, our three main variables are u, delta and omega. U, delta and gamma. Gamma we have already found out through physical arguments. Now we found out u multiplied by delta, and so we need one more equation to find out both u and delta, and that equation is the momentum balance equation. So if we write down the momentum balance equation at steady state, this is just 4 by 3 d by dx of u squared into delta is equal to, if you remember, this was written in, we have written this many times before, so let's go backwards just so that we start with this. So we have written it here also. So you can just see it's g delta sine of beta minus beta m divided by cos beta. And for the time being, I'm going to just neglect friction. So just as a simplification, you can write it like this. But what I'd like to do is I'd like to replace this one, instead of writing it like this. Let me just go back further, a little further back in the notes, so this I'm writing in terms of beta m, but for this particular problem, it's probably better to write it as in another form. So we look at the original equation, go right back, and we can look at this equation. Okay, so we can take this equation along with so I'm going to paste this equation there and then simplify it. So we have this thing to start with. So this is our equation, the general equation. And now we can remove some of the terms. So because we are looking at steady state, so this term goes to 0. And since we are looking at no friction, so this term goes to 0. So then now we are just left with, as I wrote down, 4 by 3 d by dx of u squared delta is equal to g delta into sine of beta minus mu m cos of beta. Now if we look at the condition of stress at the interface, and again I'll go backward right up to where we had actually written down this equation. So the balance of stress at the interface gave us this equation. So I'm going to copy this. So this equation that I'm going to write down, this is an equation which tells us that the shear stress, so the left hand side, this is the shear stress in the flowing layer, this is the shear stress in the packed bed. Many things cancel out. And so this is, you have CD gamma dot squared plus G cos beta into mu s is equal to G cos beta into mu m. So in other words, what I'm trying to say is I can replace mu m cos beta in terms of mu s cos beta and gamma dot squared. So if we do that, then what we will have is that 4 by 3 d by dx g delta sine beta minus, now instead of mu m cos beta, I can write this as mu s cos beta, and then you'll have one more term, which is the term due to the collisional stresses, which is CD into gamma dot squared, that is the velocity gradient squared by g. So you have essentially this type of expression. Now the reason I wanted to put it like this is that, it's more convenient to think in terms of mu s rather than mu m in this particular problem. And you'll see that, it sort of gives us, eventually you'll get exactly the same result, but it just makes things a little easier here. And so now if I combine this, if we write mu s is equal to tan of beta s, then we can combine the first two terms, and what we will get then is that 4 by 3 d by dx of u squared delta is just equal to g delta into sine of beta minus beta s divided by cos of beta s minus cd gamma dot squared into delta by g into delta. The g cancels out. So this is what you get. So here, it's just like here, if we look at, I'm going to do one more transformation, but so then I'll tell you what these things are. Now, what we can say also is, instead of gamma dot, we have gamma dot is nothing but 2u by delta. So now I'll have essentially uh, an equation that has only u and delta, that because I want to eliminate one out of the others, out of that. U squared delta is equal to g delta sine of beta minus beta s divided by cos of beta s minus c into d. Now this becomes 4 u squared divided by delta squared multiplied by delta. So then there's just one delta at the bottom. So this is what our momentum balance equation looks like. This is in terms of u and delta. Now I know what is already from my continuity equation. I know what is u delta and I know what is du by du d by dx of u delta. So what I'll do is I'll expand this a little bit, and I can write this as 4 by 3. Now I'll split this into two terms and I'll make it as u into d of u delta by dx plus u delta into du by dx is equal to g delta sine of. I'm just trying to combine the two equations, the continuity equation and the momentum balance equation, by essentially I'm going to substitute for this term, which comes from the continuity equation. So now what is d of u delta by dx? We know that is simply equal to, we see that du delta by dx is just equal to minus of omega x. So here what I'll get is, I'll multiply throughout by 3 into 3 by 4 and take this on the other side. So I'll get u delta du by dx is equal to 3 by 4 g delta cos beta s minus cd minus 3 cd into u squared by delta, and then here when I substitute for this term, it is just minus omega x into u, and then there it becomes plus. So in some sense, this term is just the acceleration. And now if I divide throughout by delta, then I'll get u into du by dx is equal to 3 by 4 into g sine beta minus beta s divided by cos of beta s minus 3 cd into u squared by delta squared plus omega x into u. So this is the equation, the momentum balance equation, and it's largely in terms of u. There's only one term that has delta in it. Everything else is only depends on u. Now if you look at what are these terms, so then you think of this as the net driving force, and it is essentially gravity minus friction. So gravity is driving the flow, and the friction in the flowing layer given by mu s is resisting the flow. So you must have beta greater than beta s. And then of course, what you have, the second term, this term is essentially the collisional resistance to the flow, and u by delta is something like the shear rate. And then finally you have this term, and this is the change in momentum due to the particles which enter the stream. So we have seen that there are certain particles which are constantly entering the stream here, so they bring some momentum with them, and that's why it alters the momentum, and when they leave, they remove some of the momentum. So this takes into account the momentum of the particles entering and leaving the layer. So this is tells you the total physics of this thing. And now, there are several examples, several ways you can try and solve this. But one way could be that, so,
Sir,
yeah, go ahead.
omega x u by delta is this.
It should be by delta.
The last term omega x u by delta.
But why delta? No, wait. So I just I did a lot of this thing. So basically, it is this term that I'm taking care of. And if I see this, this is just if I substitute for d by dx of u delta. Now, so that from the continuity equation, we already know that d by dx of u delta is minus omega x. So that means this term is just equal to minus u into omega x. And then I've just taken it on the other side. So I multiply by 3 by 4 and take it on the other side. Is that okay? So I've not divided by delta. Oh, I have divided by delta.
Last term.
I have divided throughout by delta. So it has to be divided by delta. You're correct. This has to be divided by. Oh, sorry. So correct that. It's perfectly correct what you're saying. So this is the net driving force. Thank you. Yeah, I would have had a hard time solving this if I hadn't divided by delta. Okay, so that's correct. So let me continue with what I was trying to explain. So this is the acceleration. And this acceleration depends on the net driving force. This one is the collisional friction or collisional resistance. and this is the momentum due to the influx of particles through the interface. So this is correct. So now what I want to do as a simplification, let us suppose that the acceleration is very small. That as a first approximation, we can solve this by saying du by dx is almost equal to 0. If we do that, then you can clearly see that if the first term is 0, then you have an equation which is a quadratic equation in u divided by delta. And so you essentially will have an equation which is something like 3 CD into u squared by delta squared minus omega x by delta, minus omega x into u by delta minus 3 by 4 g sine of beta minus beta s cos of beta s is equal to 0. So this is what, and this is the equation that you'll get. So you can clearly see this is a quadratic equation in u by delta, and so you know how to solve these things. So if you solve it, then you will get an expression for u divided by delta is equal to half of omega x by 3 CD, and then you'll have plus or minus of omega x divided by 3 CD whole square plus GA divided by CD, this term in square brackets raised to the power of half, and then this. So this is just solving the quadratic equation. And so now we have actually two results. One says that u multiplied by delta is just given by a function of x, r squared minus x squared. And then u divided by delta is another function. And over here, a is a known constant, which is equal to sine of beta minus beta s divided by cos beta s. So this is just that function. So put, instead of this whole thing, you just call it as a. So here you have a result, and now you can substitute for delta. We know that you know that delta is just u times delta is, we have seen, omega by 2 into r squared minus x squared. So then obviously delta is just equal to u, I'm sorry, omega by 2u into r squared minus x squared. So this is what it is. Now if you substitute for delta in there, then you can easily get, so you will get essentially an expression for u, and then you can get an expression for delta also. So if you substitute and then simplify, then you will get u is just equal to omega raised to the power of half into r squared minus x squared raised to the power of half divided by 2 into the same thing, what I've just written down, omega x divided by 3 CD. So here I had put plus or minus, but since u by delta has to be positive, you can't have the minus sign. So you must use only the plus sign, because you must have u by delta always positive. So that's why here there's always the plus sign. I'm just doing a little bit of algebra, there's nothing. So here all I've done is substituted for delta in this equation over here. And when you do that, you'll get a term which has u squared. You simplify and then take the square root. So then, what you will get is that you'll have this whole thing also raised to the power of half. So this is what is u. And similarly, now you can, what is, if you know u, you can put it in there and get delta. And so delta just turns out to be omega into r squared minus x squared raised to the power of half into omega x divided by 3 CD plus this whole thing and this raised to the power of minus half. So these look a little bit complicated, but you can simplify things a little bit more. And one way of doing it is trying to find out, what do these terms really mean? So how do we decide on the magnitude of the various terms? So supposing you define a dimensionless the nice thing about putting everything in dimensionless terms is then you'll know what is the magnitude of each term. It'll all be each of the terms with overbar on them, they're dimensionless, and they'll all be less than or equal to 1. So let's say the dimensionless velocity is u divided by omega r, which is the characteristic velocity here. Let's suppose x bar is equal to x divided by r. And then let's call a new variable s, which is the size, which is just d divided by r. And as before, let's define the Froude number, fr, to be omega squared r by g. Okay, and now if we substitute for all of these in there, uh, what you will get is that u bar is equal to 1 minus x bar squared raised to the power of half by 2 into x bar divided by 3cs plus x bar by 3cs whole square plus I'm sorry, I'll just give you the final result so that, so if we do all the simplifications and all, then what do we get? Um, Instead of doing the intermediate things, I'm just giving you the final result, and then we can look at it in more detail in the next class. So you have this term as the prefactor, and then you'll have x bar plus x bar squared plus 9CSA divided by the Froude number raised to the power of half, and then this whole thing raised to the power. So this is what you will get. So now what happens is that you see, I mean, like we could have done this even in the earlier equations, but you get something quite simple, and we can see now what we had said is that when Froude number is 1, uh, you essentially have centrifuging. But in the rolling regime, you'll have your Froude number is typically around 10 raised to power minus 3. And since everything else is quite of order 1, what happens is that because this term is so small, and then x and x bar and x bar squared are of the order of 1, then this term is huge compared to both of these terms. So then, in the limit of this Froude number being very much larger than, very much smaller than 1, so for FR much less than 1, your U bar simply reduces to half of A divided by CS into FR raised to the power of 1 by 4 into 1 minus x bar squared raised to the power of half, and your delta bar also becomes very simple, and it is just CS FR by A raised to the power of 1/4 into 1 minus x bar squared raised to the power of half. So you get these very simple results for both the velocity as well as the layer thickness. And you see that the profile is just square root of 1 minus x squared. And if you multiply both of these together, then of course u bar into delta bar, it should give you just a parabola, which we have found earlier. So you just get r squared minus x squared, but in dimensionless form, if you multiply these together, you will just get half of 1 minus x squared bar. Okay. So this essentially says a little bit about how we can get these flow. Uh, you know, even though we made uh, several approximations and so forth, uh, we will show that you don't need to make this approximation over here, and you can even just use this expression directly. I mean, it's just a algebraic expression. You can use this, and then you can get delta also for this thing, and you can compare to experiments. So in the next class, I want to just show you all of these examples that we have done, how these equations compare to experimental systems and how well they can describe the experimental system. Okay, so with that, let me end the class, and I look forward. Is tomorrow a holiday by any chance?
Yes, sir.
So tomorrow there will be no class. I'll see you now on Thursday. And on Thursday we'll have a short quiz.